So the last video ended with this article. This article was basically oxybenzone shows carcinogenic activity. And oxybenzone is one of the major players and major ingredients in sunscreen. The whole reason we use sunscreen is to prevent things like skin cancer. But could this skin cancer be really generated by the sunscreen that we're using and not the sun UV rays that's given off? Well, we already talked a little bit about this, right? We talked about the study, we talked about the concentrations that were there, and it was targeting male and female populations a different way, but it was targeting both of those populations of rats. Here's a different kind of study with oxybenzone. This is basically a fish embryo, and they started taking a look at the way the fish began to hatch and grow. And they grew these embryos in oxybenzone, high levels of oxybenzone, and some other components as well. But what they discovered is that the ones that were growing in oxybenzone actually had an effect on the hormone characteristics. And when these baby fish were born, they were actually already sexually mature. What? Yeah. Imagine you giving birth to a baby girl, and at birth, that baby girl could already have a baby. Oh my goodness. Could you imagine the world? Well, that's what was going on here. That's what was going on in this fish study that was using oxybenzone as one of those components that they were doing. Oxybenzone and BP1 act like estrogen, causing the egg protein to be produced in fish embryos. This egg protein should only be produced by sexually mature females. So if this is happening in a fish population, is oxybenzone playing a role in our hormone as well? I mean, that's always the question, isn't it? I mean, it seems like we do these studies like for rats, and we do those studies for rats first, and then if it turns out to kill all the rats, then we're like, well, it's not safe for humans. And then now we have basically a fish population. We're doing the same thing there. We're seeing a disruption. Are we questioning, oh, well, oxybenzone, what is it doing to humans? Not really heard any major statements about it, have you? Study in 2016. Results show adolescent boys with higher oxybenzone measurements had significantly lower total testosterone levels. An independent study basically took a population of boys, gave them oxybenzone, measured their testosterone, and it showed that it was way lower than normal. That's a hormone, isn't it? This is a hormone, isn't it? But we can still sell it in a sunscreen. I can still take my children in middle school, slather sunscreen all over their faces, out of everybody, all over theirs. But yet we have a hormone player here that begins to mess with their testosterone levels. Here's another study, 2017. Studied oxybenzone during the pregnancy and birth outcomes. Pregnancies in women carrying male fetuses had higher birth rates. Those babies were fatter. If the baby was a female, those had much lower birth weights than average. Kind of anorexic. Well, what's the important thing about this? Well, it's a pregnant mother. We slathered sunscreen that had oxybenzone on a pregnant mother. That oxybenzone absorbed through her skin and actually made its way to the baby that she was carrying. And we have an effect on birth weight on both sexes, male and female. Did you hear about that study? 2004, oxybenzone exposure produces significant decrease in testosterone in men and a minor increase in inhibin B, which is a sex hormone. Ladies or guys, if you're men at the house, don't seem to be interested, maybe you need to quit slathering the sunscreen on them. I mean, that's basically what this is saying, isn't it? Again, it's playing with people's hormones. A study in 2008 and 2010, 4 sunscreen filters along with oxybenzone has been detected in women's breast milk, which may suggest that the developing fetus and newborns may be exposed to these substances. 85% of the breast milk sample tested positive. That's breast milk, not break milk. Again, another study on oxybenzone, another study showing that it's absorbing through the skin, and this time it is actually found in breast milk of a mother. Did you hear about this study? I bet you didn't. Was this ever plastered all over the news? Probably not. But what happens? You keep buying the sunscreen, you keep slathering it on, you don't look at the ingredient labels, and those ingredient labels, I almost guarantee you at your house right now, if you have any, will have an oxybenzone component. Here's basically an image showing how oxybenzone can play a role in different stages. All of these are from studies that have been done in a laboratory. Studies that have been done in laboratories that are not owned by the cosmetic industry. Studies that are done in laboratories that's not owned by the FDA industry or organization. Most of these studies come from researchers whose last names are up at the very top, and then the year that they discovered this is also listed up at the very top. And most of these researchers are from independent laboratories, such as academic universities or medical schools. FDA. Zinc oxide and titanium dioxide are safe. But we see these other reports that are coming in now, and these other 12 common ingredients, there just isn't enough data to determine whether they're safe or not. We also have concerns about oxybenzone's substantial skin absorbance now. After all these years, remember, back in the 1980s, it was starting to get used. But now they have concerns on the skin absorbance, and we should take a closer look at this. They also made another statement. Available literature indicates that oxybenzone is absorbed through the skin at a greater extent than what we previously understood. Folks, this basically is saying that the FDA allowed sunscreen to be sold to the consumer for 30 years or more. And only until recently have they taken an interest to look at oxybenzone and its cousins and to give us a statement that says greater extent than previously understood. It absorbs through skin. It's found in mother's breast milk. It's absorbed through skin, and it seems to play a role in body weight compared to newborn babies. It seeps through the skin and begins to play a hormonal role as far as testosterone goes, especially in men. And it absorbs through the skin, and in a rat population at least, could create cancer. and this is the best the FDA can do? Oh, well, for the other 12, there isn't enough data to determine whether or not they're safe. Here's an article that was pulled. The FDA removed 14 of the 16 chemicals found in sunscreens from its generally accepted as safe and effective category. Notice what this statement says, though. This statement says generally accepted as safe and effective. They removed it from the category. They did not remove it from the product. So let me repeat that. Removed from the category. How many times do I have to say that? They did not remove it from the product. Okay, yeah, we've got questions on 14 of the 16 found in the product, but, go ahead and continue to use those in the product. Continue to sell them to the consumer. We are just not going to identify them anymore as generally accepted as safe and effective. Great job, FDA. Well, oxybenzone, the benzophenone family, it's not the only problem that we have to deal with, because there's also things like phthalates that are also found in sunscreen formulation. All right, so here we have Laura Vandenberg, associate professor at the University of Massachusetts Amherst School of Public Health and Health Sciences. High-level exposure to phthalates has been found to disrupt the development of male genitals. I now know I've got the guys' attention in the class. High levels of exposure to phthalates, in particular, has been found to disrupt development of male genitals. This could lead problems later on in life. But it's been found at very high doses. Sunscreen's not the only thing that has phthalates. Many other cosmetic products have phthalates as well. Meanwhile, she also did study on oxybenzone. It does affect the size of the mammary glands of mice. It also has been detected in breast milk, according to our study. And that also means that it could venture its way into the breast tissue. Now we have concerns with breast tissue. We have concerns with possible carcinogenic. We have concerns with hormone disruptors. And all of that is a magical concoction for breast cancer. However, we should always be cautious when applying the findings of mice studies to humans, said David Leffel, professor of dermatology and surgery at Yale. Oh, well, that's real funny. We like mice studies when we're trying to approve a drug that will eventually go to human, and we look at the mice population first. Is it safe for them? If so, it moves on. Is it not safe for them? Then if not, it doesn't move on. But now all of a sudden, we only want to listen to mice studies when it actually tells us something good. No, you can't rely on mice studies for this stuff. Sorry, that's not the way this works. Just because it happens that way in mice doesn't mean that it's going to happen that way in human. We'll tell all of the other clinical trials that. Again, we have a problem. Number 3, the common sunscreen additive vitamin A may also speed the development of skin cancer. That's right, folks. A vitamin A that's added to many of the sunscreen products and many other cosmetic products as well has a strong tie to speeding up melanoma. So not only do we have to worry with oxybenzone, but we also have to worry with all of the other ingredients that come along with this as well. And now you know the story with sunscreen. All right? This is a big questionable mark field at this point in time, because sunscreen Well, it should be safe. Sunscreen is doing a job that we want it to do to prevent cancer. We do not want to slather in a lotion or an aerosol or a gel only to get complications later on in life. Now, how much? That's the question. How much oxybenzone actually causes these side effects? Well, that's a different discussion. How much do you have to slather on in order to get these side effects? How much do you actually have to use for it to be detrimental to you? Well, in some cases, you would have to use it every single day and slather it on from head to toe for 30 years before you would find a problem. But at the same time, the FDA kind of knows we need to take a closer look at this stuff. Especially with oxybenzone, because it absorbs a little bit better than what we thought. It actually absorbs into the skin. It doesn't just stay onto the surface of the skin like we expected. So what are you going to be doing in this lab experiment? So here's your procedure. That's right, not multiple pages of crap. Just really 2 paragraphs. That's it. This first one at the top, which is basically the standard prep. And the standard prep, quite often, you probably will not have to do. So you need to question that when you come into the lab, and you need to see if these standards are already prepared. And if they are already prepared, they've probably already been ran on the instrument. And second, you'll see samples. You're going to prep some samples. Well, how do we do this? Well, we're going to take a half a gram of sunscreen. So 0.5 gram is 500 milligrams, give or take a little bit. We're going to weigh that out into a container in our lab, and then it says dissolve that in HPLC grade methanol. All right, so methanol makes a great solvent. Methanol is also a very common mobile phase for this instrument, so it goes hand in hand. Great solvent carrier, great mobile phase for my instrument, not a problem here. It's good, all right? Well, HPLC grade just basically means lower contaminants. That's all that means. We pay a little bit more extra for extra clean HPLC that will not have contaminants that absorb in a column or absorb with a common UV detector that's on an HPLC instrument. All right, so it says take 500 milligrams of this, dissolve it in methanol, and then you are going to bring that to a total volume of 100 milliliters. When you do that, this is way too strong. Okay, there's going to be too much oxybenzone here in order to measure. So we're going to take this amount, and it says take 2 milliliters of that sample and then dilute that to a total of 10. So a 2 to 10 dilution is what we'll end up doing. So whenever you get the part per million from your calibration curve in this lab experiment, that part per million is from the weaker solution that you have made. That weaker solution came from a 2 mil pool that was 100 mils in total. So you're going to have to do a back dilution here. All right. And again, it seems like this is always a common problem for people, but it shouldn't be, because look, CV equals CV. This part per million will be the concentration of your sample that you made as far as the weaker one goes. So let's say, for instance, this shows up to be a 10 on the instrument. Well, this is your concentration of the final. You made 10 milliliters of that. So 10 ppm, I made 10 mils of it. That is what was ran on the HPLC instrument. I want to know, what is the concentration of the original, the one that I started with, if I made 100 mils of that stuff? That's what we're after here. All right? And nope, I almost told you wrong. Look at that. This is not 100 mils. This was pulled. Look, I did the same mistake that most people do that I just griped and moaned about, right? What most people do is that they use the wrong volume. So this is actually 2, all right? So I have 10 ppm for my machine. That represents the 10 mils in total that I made. So I want to know, what was the concentration of that 2 mil pull? Because that concentration represents this amount that I've made. So 10 times 10 is going to be 100. 2 times x is 2x. Divide each side by 2. And x is going to be 50. That is how we back dilute. All right? So this is the total volume that I ended up with, and this is the volume that I pulled. 2 mils. What was the concentration of that 2 mils that I used to make that solution with? All right, so let me kind of give you an example of the spreadsheet at this point and then talk about some of the calculations, because as we can see, this is a pretty simple sample prep technique here. So this is what your spreadsheet template is going to look like. It's very similar to all of the other ones that you've had from me so far. So you're going to see the area for part per million and the area from your IC chromatograms. That's going to go over here. You'll plot your regression line, of course, that will go here. And then down at the bottom, this is where your sample information is going to go. A couple of things about the sample calculations I would like to clear up for you at this point. The area, of course, you'll know where to find that. That area is going to come from your chromatograms, and that area will be plugged into your regression line in order to solve for a concentration, and that concentration will be right up here. All right. Okay, so that part per million represents your weak one. So you're going to have to do a correction factor for your undiluted part per million. That undiluted part per million, we've already talked about how to do that. That's CV equals CV. You'll know this concentration. You'll know that volume. That came from a 2 mil pull, and you need to calculate the concentration that was there when you pulled it. Okay, so that's the back dilution step. The sample weight's going to go ahead. It's already pre-filled into the spreadsheet for you. This is how much sunscreen that was actually weighed out for that particular sample. So 521.3 milligrams. The next column is going to be milligram of the oxybenzone. This represents the milligrams that's going to be in your sample, which is the 100 mil sample, right? We took 0.5 grams, dissolved it into 100 mils. So basically what that means is I need to take my undiluted part per million and realize that's milligram per liter. I want to know how many milligrams are present in 0.1 liter, because that's actually what I made. I want to know how many milligrams are in that half of a gram sample that I weighed out and diluted and dissolved in the laboratory. So that is what that calculation represents. That is another kind of ratio, proportion, cross multiply and divide calculation. So once I solve for my ppm, that's that many milligram per liter. I didn't make a liter to run it, right? I made 0.1 liter. So how many exactly is in that 100 mils? Finally, the actual percentage of oxybenzone. This is a straightforward calculation that takes the milligrams of oxybenzone that you get from that prior calculation from up above, and you're going to divide it by the milligrams of the sample that you started with. And in this first line, it's 521.3. That's why we went ahead and converted this to milligram, because we're going to take milligram of oxybenzone, divide it by milligram of my sunscreen in total, and we multiply that by a 100 in order to get a percentage. So this is the actual percent of oxybenzone. I've also pre-filled in the theory percentage of oxybenzone for you. So this is basically coming straight from our label. This is the way that it is, and hopefully our numbers kind of match that. If 6 is the cap, if it doesn't match the 6 here, and let's say it was way more, then they are probably in violation of their labeling, and they're also in violation of their formulation as well. So there's too much or there's not enough that's present that's on the inside. And then finally, for the error, you calculate the error just like always, right? You take the absolute value, preferably, of your number minus the theory number divided by the theory number, and you multiply that by 100 in order to calculate percent error. Okay, so if you do get a negative, that just means that you're on the other side of the value. Doesn't necessarily mean it's a negative value. And the reason that I'm telling you to take absolute value here is because we're going to do an average. And in order to do a proper average for error, we assume that all of the error is going to be positive. You can't have a negative error and a positive error and have them cancel each other out, right? You screwed up on one run, you screwed up on the second run, so therefore you're going to average your screw-ups. You can't go way, way low and then way, way high and then have it cancel out to make it zero. That's not really good lab data, okay? All right, so there's the calculation. There's the spreadsheet. That's really all that you'll have to do. If you notice down here in the sample information, there's 3 different categories. Those 3 different categories represent 3 different samples. They were analyzed twice, and you're going to average those 2 together. So you're going to average the actual percentage of those 2 and the average error of those 2. And then you'll do a separate average for the second set and then a separate average for the third set. So you'll have 3 averages here and you'll have 3 averages there. One representing actual percentage and the other one representing error percent. All right, so treat each one of them separately. Do not do an overall average because they are different samples. You cannot do that. You have to treat them separate because they're different ones. They come from different bottles, and they all have a different percentage that's stamped on the label. So that's all there is. A back dilution calculation, a proportion ratio based on the 100 mils that you prepped, not the liter, and then a calculation on percentage. Just take the portion of oxybenzone, divide it by the milligram of the total sample times the 100. All right, so good luck with the lab. As far as the lab data is concerned, this is what you're going to see. All right, so up here at the very top, you're going to see at the very, very top, it says sample name, and for this very first one, it says 12 ppm. This was the standard that was made for that particular year. So that's where you're going to find the sample names up here at the very top. You're also going to see the date and time that they were ran. Over here to the right-hand side, it says injection volume, and it says 10 microliter. So for this particular year, they injected 10 microliters of sample onto the instrument and then ran it. Here's the chromatogram for that particular standard. Notice the very large peak here at 1.428. This is a standard of just oxybenzone. There's a little bit of contamination that's probably here. This is not a big issue, or this is not a big deal because nothing that we order really is 100% of anything. But there is the small trace of contamination on the baseline. So 1.428 is truly the oxybenzone peak that you're going to be looking for. If your sample does not have a peak at 1.4-ish, and it's like 1.2-ish or 1.1-ish or 1.6-ish, then that is not oxybenzone. You do not look at those areas, all right? Up here at the top, you also see some data about the wavelength. Notice this wavelength says 254. This is very common. This wavelength at 200 or 254 is very a good wavelength for benzene-related compounds. And we already know there's 2 benzene rings in something like oxybenzone. So there's your standards. They're going to show up in the very beginning. And then after your standard set, you're then going to see some samples. Notice, too, how we get bigger and bigger in concentration. Those contaminant peaks get smaller and smaller. And the reason is because at the super low ppm values, we are really close to the baseline, and those are more exaggerated. They show up a little bit more. And then as we run it, this peak for oxybenzone gets larger, of course, and that larger peak is giving a smaller contaminant in the very end as far as the shape goes on the chromatogram. But then we're going to get to some sunscreens. And this is what sunscreen is going to basically look like. There's going to be multiple peaks. And one of the reasons is because sunscreen has multiple components, right? Not just oxybenzone, but you saw those ingredient labels. There's going to be tons of different things on the inside of that. So for that reason, we're going to be expected to see tons of different peaks. But only one of these will be oxybenzone. So you'll have to use your standards, figure out a retention time. That retention time is also going to be the retention time for oxybenzone and all of the sunscreens that you run as well. the same traditional story for chromatography over and over and over. Again, up here at the very top, you're going to see the sample name, DMJ Equate, for this one. So basically Walmart brand, and this is what it showed. It also lets me know that it is more than just oxybenzone. All of the other common additives for sunscreen is probably showing up here. And we could do studies on those if we wanted, but we're only going to focus on one of those. I think that's good enough, and that one is going to be oxybenzone. All right. Okay, so here we get another chromatogram. Notice that this chromatogram's been shifted a little bit. This is a 1.551. This is actually oxybenzone for this one. So just kind of go into that with that realization. This 1.551, that is a shift in retention time. Everything has been shifted. It's probably due to equipment or instrumentation or tubing or the column. A number of different things can go on as far as retention times and having them shift between one run to the next. So just keep that in mind. But here we kind of go back to normal. So that's the way that you'll interpret the data. Good luck on interpreting the data. If you need questions, you just need to send me an email, let me know, and maybe we can work through it and get you a good spreadsheet with some really good data. So this template is up. You're free to use it, and you're also free to make your own if that's what you like to do. I don't know why, but you're more than welcome to. So there's the story with oxybenzone, and I'm sticking to it. And sunscreen, the next time you slather it on yourself, just kind of pause for a minute, think about what you're doing, and then when you go to the store to buy your next sunscreen, you need to kind of question, do you really want those sunscreens that have the oxybenzones and related compounds in them? Or do you want to go the old-fashioned way and get the zinc and the titanium and have a nice ghostly white sheen on you, right? Nothing's ever perfect, and sunscreen's not either.